Right now, somewhere in the Atlantic Ocean, a ship is dragging a grappling hook across the seafloor, trying to snag a cable the thickness of a garden hose that carries more data than all the satellites in orbit combined. When you load a website hosted in another country, or stream a video from a different continent, or send an email halfway around the world, there's a 99% chance your data is traveling through a cable on the ocean floor. Not satellites, not wireless, cables. Over 1.4 million kilometers of them, lying on the seabed, carrying roughly 99% of all international internet traffic. And despite being submerged under thousands of meters of seawater, subjected to immense pressure, occasional anchor strikes, and the occasional curious shark, they work continuously for 25 years. The engineering required to make that happen is more intricate than most people realize. Because here's the thing, you can't just drop a cable into the ocean and hope for the best. The water alone doesn't conduct the light signals, so you need repeaters every 50 to 100 kilometers to boost the signal. Those repeaters need power, 8,000 volts of it, which has to be sent through the same cable carrying your data. The cable has to survive pressures exceeding 800 atmospheres in the deepest trenches, resist corrosion for decades, and be flexible enough to coil onto a ship, but rigid enough not to kink. And when something inevitably goes wrong, a fishing trawler snags it, an underwater landslide buries it, a shark bites it. You need to locate the break, send a ship to a precise spot in the middle of the ocean, fish the cable off the seafloor, splice in a replacement section, and lower it back down without severing anyone else's connection. Let's start with the cable itself. At the center are the optical fibers, strands of ultra-pure glass about 125 micrometers in diameter, roughly the width of a human hair. Each fiber can carry multiple wavelengths of light simultaneously using a technique called wavelength division multiplexing, and modern cables bundle 8 to 16 fiber pairs. A single fiber pair can transmit over 20 terabits per second. For comparison, that's enough bandwidth to stream roughly 5 million Netflix videos at the same time. The glass is so pure that if seawater had the same clarity, you could see to the bottom of the Mariana Trench. Those fibers are embedded in a steel tube filled with petroleum jelly to block water. Around that goes a copper or aluminum tube that serves as the power conductor. Because every 50 to 100 kilometers along the cable sits a repeater, a sealed cylindrical unit about the size of a large propane tank, packed with optical amplifiers and power regulation circuits. These repeaters boost the light signal, which naturally degrades over distance, back to full strength. And they all run on roughly 8,000 volts DC, supplied from shore stations at both ends of the cable. The current flows out through one conductor and returns through seawater, completing the circuit. If a repeater fails, the entire cable segment goes dark until a repair ship can splice in a replacement. Around the power conductor comes the armoring, and this is where the cable's design diverges based on depth. In deep water, beyond about 2,000 meters, the cable is relatively thin, about 17 millimeters in diameter, and consists mainly of steel wire strength members and a polyethylene sheath. There are no predators down there, no fishing activity, and the seabed is mostly soft sediment. But in shallow coastal waters, the cable can be as thick as 200 millimeters, wrapped in layers of galvanized steel wires, polycarbonate, and sometimes additional external armor. This is because the continental shelf is where the threats are. Fishing trawlers dragging nets, ship anchors, rock outcroppings, and yes, sharks. Multiple submarine cables have been damaged by shark bites, possibly because the electromagnetic field around the power conductor resembles the bioelectric signatures sharks used to hunt. Some cables are now sheathed in Kevlar-like materials specifically to resist bites. Laying the cable is a feat of precision navigation. A cable ship, essentially a floating factory with massive storage tanks that hold thousands of kilometers of coiled cable, follows a meticulously surveyed route. In shallow water, a remotely operated plow buries the cable 1 to 3 meters below the seabed to protect it. In deep water, the cable is simply lowered to the bottom. The ship moves at roughly 6 to 8 kilometers per hour, paying out cable at a rate carefully synchronized with the ship's speed and the seafloor topography. Too much slack and the cable loops and tangles. Too much tension and it snaps. The ship must account for underwater mountains, trenches, and the curvature of the Earth itself when calculating the required cable length. A transatlantic cable, for instance, might be 6,600 kilometers long even though the straight-line distance is only 5,500 kilometers, because the cable has to drape over the mid-Atlantic ridge and settle into valleys. The route itself is a compromise between distance, geology, politics, and risk. Cables avoid underwater volcanoes, earthquake-prone fault lines, areas of frequent anchor strikes, and occasionally naval exclusion zones. They land at beach manholes or in protected bays where they transition to terrestrial conduit and connect to shore stations. The landing process is delicate. The cable has to be pulled ashore by divers or specialized equipment, and the endpoint must be precisely positioned because once the cable is in the water, rerouting is prohibitively expensive. In some cases, permits and environmental reviews take longer than the physical installation. Now, when a cable breaks, and they break more often than you'd think, averaging 100 to 200 faults per year globally, the repair process is a masterclass in marine engineering. First, the fault has to be located. Engineers send test signals from both ends and measure the reflections to triangulate the break, usually to within a few kilometers. Then a repair ship is dispatched, which can take days or weeks depending on weather and the ship's location. Once on site, the ship deploys a remotely operated vehicle or a grappling hook on a steel line to snag the cable and haul it to the surface. This can involve dragging a hook across kilometers of seafloor until it catches. Once the cable is on deck, technicians cut out the damaged section, splice in a new segment complete with its own mini repeater if necessary, test the fibers, and lower it back down. The entire repair can take a week and cost hundreds of thousands of dollars. But the alternative, leaving an entire cable system offline, means whole countries losing connectivity. And here's a detail most people miss. The internet doesn't rely on individual cables. Major routes like the transatlantic corridor are served by dozens of parallel cables, owned by different consortia. Google, Facebook, Microsoft, Amazon, and traditional telecom carriers all operate their own. If one cable is cut, traffic automatically reroutes through the others, often without users noticing any slowdown. But in regions served by only one or two cables, parts of Africa, the Caribbean, island nations, a single break can knock an entire country offline for days. In 2008, a ship's anchor severed two cables in the Mediterranean, cutting internet access for 75 million people across Egypt, India, and the Middle East. The geopolitics of submarine cables are quietly significant. Whoever controls the physical infrastructure controls the data, which is why governments pay close attention to who owns, operates, and has access to cable landing stations. The United States has historically been the dominant player, but China is now funding cables across Asia, Africa, and the Pacific, often as part of broader infrastructure initiatives. Russia has been suspected of mapping cable routes for potential sabotage, and in 2022, several European cables experienced unusual interference that some officials attributed to Russian underwater activity. A single severed cable can be an accident. Multiple simultaneous cuts start to look like strategy. There's also an environmental angle. Cable routes are now planned to avoid coral reefs, whale migration paths, and marine protected areas. But the electromagnetic fields and the installation process itself can disturb sediment and benthic ecosystems. Decommissioned cables, hundreds of them, no longer in use, are often left on the seafloor because removing them is more disruptive than leaving them in place. They become, in effect, permanent fixtures of the ocean floor. And as demand for bandwidth grows, more cables are being laid each year. By 2030, the total length of submarine cables is expected to exceed 2 million kilometers. That's enough to wrap around the Earth 50 times. So the next time you stream a video or load a foreign website, remember, your request is likely traveling as pulses of light through a hair-thin strand of glass, inside a cable armored against sharks and anchors, lying on the ocean floor, kept alive by 8,000 volts from a shore station thousands of kilometers away. It's one of the most ambitious and underappreciated feats of engineering on the planet. If you found that interesting, subscribe for more breakdowns of how the world's infrastructure actually works.